Hello, everyone. Welcome back again to the lectures of offshore positionings and Institut Teknologi Bandung and Geodesy and Geomatics Department. Um, that's Fikri Muhammad. Now I'm going to deliver about the next modules of Module 12. It's about the aided inertial navigation system. So we've talked previously about the inertial navigation systems and the inertial navigation sensors, and also the basic, which is the reference frame that normally discuss or normally use in inertial navigation systems. Now we're going to talk about the inertial navigation system, because as we know that relying only with the inertial navigation system, it's not enough. So we have to integrate it with another sensor. So that's why it's aided. I mean, it fused with another sensor. For example, for drone navigations, it's fused with GPS and etc. All right, now we're going to talk about the navigation parameters and yeah, in the aided inertial navigation systems. Or yeah, for background of aided inertial navigation system, or sometimes also called as AINS, it relies basically on the sensor fusions of INS with the external sensor. In this case, if we're going to talk about the offshore positionings, for example, for the underwater robots for AUV, then we're talking about the integration between INS with acoustic positioning system with APS, for example, or optical sensor or camera or lasers. So it's basically to reduce the drift, because we know the gyroscope and accelerometers from IMU that create a system as INS have always the bias and noise, right? So it's, if we're relying on that measurement over time, the drift will be accumulated, and of course this drift that accumulated will affecting our positioning accuracies later on. So of course we want to increase our positioning accuracies. So in this case for AUV, where is our INS system? Our INS system is here, the AHRS, the MEM sensor. And it's not that common, but it's also integrated with the FOG, the fiber optic gyro, but because it's separated, we have to calculate the relationship between them and also the offsets and yeah, the translation between frames. But anyway, we have here a lot of sensor in AUV, like for example, the acoustics, the USBL, yeah, the USBL and the depth sensor to calculate from the pressures, and the compass, for example, yeah, depth sensor, GPS and Wi-Fi for telecommunications, for example, or data streaming, and stereo cameras to directly measure point clouds, and yeah, DVL as an acoustic positioning system to measure the positions of the AUV, and the ACOMS or acoustic communication system to transmit the data between AUV to the motherships, for example, or the main board in the motherships. So yeah, this is, for example, the DVL and INS. DVL, Doppler velocity log, is basically somehow the same like ADCP. You probably already heard about that in the hydrography lectures. And yeah, difference with the ADCP, that ADCP is normally measuring the Doppler shifts to measure the speed of current, right? And the more turbulent waters, the more able the ADCP to measure, because it's basically measure the Doppler shifts between the sediments that transmit in the water columns. But here in DVLs, rather than pointing upwards towards the water columns. It's relying on the reflections of the sound bouncing off the seabeds. So yeah, at the end, it refines the velocity estimates for the INS. And the techniques for AINS. First, of course, we're going to talk about the sense of usage between, for example, the VL or acoustic positioning system with the INS. So we have to talk about the sensoric. And then, of course, we have the noisy measurement and noisy estimations between both sensor. Then we have to do the filtering for estimations. And then how we do the error mitigations between both, right? How we increase the accuracy between both, which is the coupling. Like, for example, here, if it's loosely coupled or it's not directly tightly integrated or loosely integrated between INS and the APS, acoustic positioning system, then of course we'll be having lesser accuracy in comparison with the deep if the both system are both deeply coupled between each other, or even if it's more tightly coupled of the systems. And of course, we'll be having the latencies because the systems are running separately in different time, and we have to do the time synchronizations because maybe the acoustic positioning system is not having the same frequency as the INS, for example. For example, the INS have 200 hertz. Training data means that it records data every seconds with 200 data. And the acoustic positioning system, for example, has 400 hertz. So it has more data in 1 second. And this huge amount of data has to be somehow merged together. And yeah, we have to deal with the latency. So the importance in the offshore positionings, of course, to increase the accuracies, because by combining the INS with external aiding systems like DVL, the AINS can significantly reduce the drift and errors that accumulate in standalone INS, because it basically has other measurements that we assume can be trusted, because the other measurements has also their limitations, for example, or their accuracies that we can rely on. And it of course helps us with real-time trackings that AINS provides the continuous real-time positioning and velocity trackings. And of course, like for example, if you're talking about the AUV has to be deployed and record the data and come back again. But how if you want to record the data for a longer period of time? So doesn't have to like manually collect the AUV, but the AUV can submerge and also can descends can and also ascends to the sea surface by itself. So it reduces the need of periodic surface-based position fix. So we don't have to like correct the drift that accumulated by the INS by sending the AUV again to the sea surface that and then connects the AUV with the global reference frame from the GPS. So we don't have to do that because we believe that the AUV with the AINS, the drift has already been minimized. So if we're going to talk about the AUV itself, the AUV will be having like problems, 3 basic problems, like how does the environment look like? How does the AUV is basically navigating in the open area, and where to go and where am I? This is basically the most important things, which states it's the AUV currently is, and for the next stage where it should go, right? And this, for example, one project that deals with the AUV for automatic pipeline detections, the comprehensive integrated and fully autonomous subsea monitoring, or called CM. This is a project running currently by the Heaven City University of Hamburg. This is the project that I and also the colleagues from the HCU is involved to do the automatic pipeline detection by using the AUV, and the AUV has somehow to follow the pipe autonomously. And of course, we can first using the electronic nautical chart, for example, that tells where the AUV should go, like for offshore surveying, for bathymetric surveying, we plan the line, but the AUV has also to follow the pipe, the real pipe underwater by integrating the sensors like cameras, magnetometers, bottom profilers, or acoustics like MBS, forward-looking sonar. And the end, it can by using all this measurement, it will tell the system where the AUV should go. And the other problems is when the battery is already running out, we have to normally manually collect the AUV. Like the AUV has to ascend first, and then we manually collect the AUV to our mother ships and then recharge it. But here, for this case, the autonomous docking systems or auto docking helps the AUV to find its way to the docking platform so that it can charge and also can do the data transmissions. And to find this way, it's basically also doing the aided navigation systems, aided inertial navigation system. So if you're relying only with the inertial navigation system, you have to follow this estimations, or we have to follow these positions towards this docking positions, then maybe it will not reach the docking platform. But if we integrate with the camera, for example, the camera will track where the docking is currently is by replacing the markers on the docking platform. Then the camera will detect the markers, and then by doing so, the camera will be integrated with the AINS, so that will be having less drift later on, and then the AUV can reach the docking and then doing the data transmission while it's underwater. So, and after doing the recharge and doing the data transmission, the AUV can be deployed again and doing the continuous pipeline tracking or data collection for further tracks. Well, yeah, of course, we'll be relying on the navigation equations like we previously discussed, right? But now we're going to talk only with the strapped down INS. Basically, we have the IMU, which is consisted consisted of gyroscope and accelerometers, and this both sensor provide the measurement data. Gyroscope provide the global orientations from the orientation measurements, and the accelerometers basically measure the global acceleration, the accelerations vector. If it's reference to the our reference frame, which is global, then we'll be having the global accelerations, and if we integrate it, and we'll be having the velocity, and if we integrate the velocity, we'll be having the positions, and later on, we'll be having global orientations, positions, and velocity from our INS systems, right? That's our navigations equations. Yeah, this is our INS, the red box, and our IMU is the green box. All right, now we're going to talk about the filtering or estimations. Of course, we do have the navigation equations, but still there are some noise, and we already calibrate our systems, our IMU, but of course, every measurement has its uncertainty, and we want to minimize that uncertainty. How we do that? By doing the filtering techniques. The working principle of aided inertial navigation systems is basically consists of 2 points, which is predictions and the update. So the INS first computes navigation solutions based on the inertial sensor data, gyroscope and accelerometers, and then it does the updating, aiding the system provide periodic corrections like positions, velocity, headings, and we do the fusion. So it's basically they are working together. every time. So yeah, first it predicts the initial state. So from the initial state, it predicts the next state, and then it fused with the measurement. The prediction is fused with the measurement, and then it provides the corrections of our predictions. And then from our corrections of prediction for the next state, we predict again, and then doing that iteratively while the AUV is moving, for example. And yeah, the estimation algorithm like Kalman filters optimally combine the data. So we're going to delve into the Kalman filters, which is most common used by the inertial navigation system for aiding the inertial navigation system equations. Right. The Kalman filter is recursive algorithm for estimating states in system. So what is states actually? States can be positions if we're talking about AUV, velocity, orientations of the vehicle of the AUV. Like for a chemical compound, it can be temperature or etc. And two sorts of informations are utilized, basically. The measurement from the sensors and the mathematical model of the system to do the predictions for the next states. So we have the initial state 0, 0, 0, our position, for example, and the velocity is also 0, and the acceleration is also, the headings is also 0, the orientation is also 0. The next state, k plus 1, for example, or time k, we do the prediction for that. So we'll have the mathematical model for doing the predictions. And in additions, we do have the accuracy of the measurements and the models, right? So the predictions cannot be always accurate, and the measurement cannot be always also accurate. As we know, the gyroscope and the accelerometer sets the noise and yeah, the bias, and that should be specified. This is, for example, the illustrations of depth tracking of the AUV with using the Kalman filtering techniques. Oh, so it's basically the true depth, which is shown as a blue line. This is the true depth, and our AUVs basically should be following that true depth. So basically, our AUV is basically in that true depth, but the measurement is showing differently, which is it has a noise, and every time the noise can be different, and our estimations by doing the mathematical model and also combined with the measurements, we'll be having somehow close to the true values, which is, yeah, not aligned, but close. Still have the uncertainty, but it's close. We minimize the noise, basically, from the measurement and also our estimations. All right. Now we're going to talk about states. Yeah, states here is, for example, the initial states of the AUV. Underwater is 0, and then the next states, this one is at time n or time k, anything, which is already translated. And while doing the translations, we have the positions, right? This is the initial position. We'll be having another positions here. We're having the velocity, and we'll be having also the heading, the orientations, right? For example, like that. So, yeah. So we're basically estimating the positions of the next states by incrementing our measurements, by incrementing our yeah, measurements from velocities and also from the rotations. All right. So the recursive algorithm of Kalman filtering starting at T0, for example, at T0 begins with the initial estimations with its covariance or with its uncertainty. Of course, we have the uncertainty. We estimate, so our initial position should be 0, 0, 0, but we estimate with our model, then it's not 0, 0, 0. It is 0 0.1, comma 0 0.1, comma 0 0.1, for example. We have the uncertainty. And then from the mathematical model and the initial state, we have the new estimations at T1. So basically, from our estimation, we estimate the next movement of the AUV as of time 1, for example. So we predict for the future steps. And then the uncertainty of the predicted estimations at time 1 is calculated from initial uncertainty. So uncertainty at we previously have 1.0 uncertainty. Then for the next one, we believe that the estimation will be also 1.0. Yeah, 0.1 uncertainty. And that will be the base of our accuracy of the model, for example. And then we chip in the measurement at time 1. Then we'll provide the new states info. Previously, our states was 0, 0, 0, and then the next one, the measurements is, for example, here in this case, for example, minus 13 meters depth, for example, our depth is 13 meters. Then, yeah, that will be our new states info. And the measurement noise and the predicted uncertainty are weighed together. So basically we have the measurement noise and also the basically the measurement uncertainty and the predicted uncertainty. So they are weighed together, and then we bring the new updated estimations at the time 1. So both of the measurement and the estimation are chipped in together to provide the new updated estimates. At the next step, that's the next time, it calculates also the same, but it based on the previous state of the previous update state. So not based on the measurement state from that time, but from combined update state. So, for example, this is the initial state of the AUV. And if the AUV moves towards the next time step, time 1, for example, we will be having the new estimations, right? So we estimate the movement of AUV from the translations, which is the positions and the velocity and the orientations measurements. Then we provide the measurement update, and then we'll be having the final estimate. But of course, for example, the uncertainty always aligns. So for example, our previous state is here, and then we predict the movement by using a model, by using Kalman filter. And then our predictions at the next time step is this one. And our measurement states is this one. So we have the predictions and measurement state together, and then we combine both to provide our corrected states. It's basically the idea of the Kalman filter is that. So basically Kalman filtering is like combining the predictions and the measurements. So we predict both of the states and uncertainty, and also measure the data and also the uncertainty, and both of them are chipped in together to have the corrected state with uncertainty from both model and measurements. We were talking a lot about uncertainty previously, right? So basically our uncertainty in this case is described by the variance and covariance. The variance is the measure of the width of distributions, like for example here, the position error distributions and the velocity error distributions. The error distribution of velocity is more spread as compared with the velocities, for example. And if we make it as an ellipse, we'll see that the positions has a greater uncertainty in positions in comparison to the velocity, because the position has greater distribution in comparison with the velocity, as we can see here, right? And from that, we can form the covariance matrix, which is the correlations between the variance. For example, the correlation between positions and positions and one position to another positions, and positions with the velocity, for example. yes, basically the square matrix with number of rows and columns equal to number state of variables, and the variables here is the position and velocity. If we add another variables, like for example, orientation, will be having three variables, right? So of course the noise, if the, yeah, this is our true state. If the noise at zero mean, then the group of measurement will all be centered around the true state. What does it mean? This is our true state, and our measurement, like we have these noisy measurements, it's not always aligned with the true state. And we have another measurement because, as we said previously, that our data, our data from our INS system has a lot of measurement per time, per seconds, for example. So we'll get a lot of measurements in one time, in one state. And if our noise at zero mean, then the group of measurements, this is group of measurement, will all be centered around the true states or the zero mean Gaussians. And if the noise was Gaussians, so more randoms, then the measurement will follow the normal probability distributions, like the previous graph, where the width of distribution or the amount of noise in the sensor is the variance, like in the previous slides. So of course, yeah, over time, the measurement will accumulate some noise. Like for example, you can see here, this is our state position, which is already uncertain, just already noisy enough. And then our next state will be having again measurements. This is our uncertain state positions, and probably our next states, the noise is larger or more uncertain final positions. We have modus noise because, and the process noise covariance matrix basically sets how fast the uncertainty grows. So yeah, basically when the AUV is moving in the linear motions without any influence from the water property states, the process noise might be constant or maybe small because the noise might be somehow the same, like from the previous position, from the previous initial positions, initial states, to the next states, the noise is somehow constant. The distribution might be similar with each other, but if the AUV is moving in a not linear motions due to, like for example, as the follows pipes, or because of the AUV has some the accelerations, and again acceleration and the motion change, of course the measurement might be different, and it'll be given more uncertain final positions. And this process noise covariance matrix basically sets how fast the uncertainty grows between states. So yeah, larger process noise basically, or larger covariance values is basically it assumes that more unpredictable systems and uncertainty grows faster and rely more on measurements. So we have to check a lot of measurements every time per second if the AUV is moving in the linear motions. But if you already define our line of measurements, then probably, and we have the constant speeds and motions over time, then the measurement updates should not be always be integrated over time, like for example, like that. But yeah, to be able to have more accuracy, of course, we have we want to always integrate our measurement data every time so that we can control our process noise, right? So we don't have to rely more on the model, but we want always relies on the models and the measurement updates. So yeah, we basically in Kalman filter we're talking about estimations. So we have the predicted states with uncertainty. So I talked about that before, and then measurement with uncertainty, and both of them are Gaussian. So both of them are random, for example. And by multiplying this Gaussian distribution together, we'll be having the optimal state, which is also Gaussians. It indicates if it has low covariance, it indicates that it has higher accuracy estimations. Like for example, previous states like this, and then prediction at the next time steps is like this, and we'll be having also measurement updates at the next state, and then we multiply both of them together. We'll be having the optimal state estimates in the center, and also the optimal error covariance, which is smaller than the measured covariance and the model covariance, as we can see here. So basically, by multiplying both of Gaussian distribution together, we'll be having the optimal state estimate later on. We'll be having more accurate state estimate because we're not only relying on the predictions, but we also chip in the measurements to bring our predictions to the context of the optimal states. So we're going to talk a bit about the equations. So we're talking about the concept of Kalman filtering. Now we're going to talk more about the equations, which is here. The states, this is our initial state, the state vector is at time k. And then we have the state transition matrix and the control input vector at tk, at time k, and then the process noise, of course. So we have the state transition matrix and the control input matrix. So this is only for general overview of the states. And then we have the measurement matrix, the measurement matrix, measurement at time k, and of course the measurement noise. It's accompanied with the measurement noise. And then we do the predictions. So we do the predictions from the previous state estimate. So we predict the state estimate before any update. So this is before any update, still have a large uncertainty, for example. It has a process noise as well. And in Kalman filtering, which is also interesting, is that we do predict the uncertainty, or we predict also the covariance. So we have the uncertainty from initial states, and then we predict the uncertainty in the next states. And yeah, here, for example, we have the covariance metric from the previous states, for example, k-1 here. And then we have the process noise. And this is, for example, if you're having the positions and velocity as state vector, we'll be having the covariance matrix 2 by 2 like this. For example, how the variance, it consists of 4 variance, which is the how position varies, which is with the positions, and how velocity varies with the velocity, and how velocity varies with the position, and vice versa. And then what's important in the Kalman filtering is Kalman gain. So basically we have the Kalman gain, that the key of part of the filter is update state. So this is very important in the update state, which is combine the previously predictions with the current measurements to have the optimal state later on, right? To have the better state estimations. So this is our Kalman gain, and then it basically determines how much the current measurement should influence um, the update state estimates compared to the previous to the prior predictions. So we already have the prior predictions, and we want to know how the measurement should influence the estimations. Is it that much? So the larger value of Kalman gain, meaning that our estimation is not accurate because we have to rely more on the measurements, right? So if it towards or biased towards the measurements, the Kalman gain, meaning that yeah, our estimation is not that correct. But if our Kalman gain is small, meaning that our estimation, oh, it's good enough, then we can continue with another next estimation steps. Then of course we have the previously covariant matrix or the predicted covariance that represents the uncertainty of state estimates before we incorporate that with the current measurements. And yeah, we have the transpose of the observations matrix, or yeah, it basically maps the state vector into the measurement space. So its transpose basically helps to transfer information from the measurement space back to the state space. So we want to transform the informations uh, from the measurements to the state. So yeah, we want to chip our measurement to uh, uh, our models basically. And this one is basically the projected error covariance in the measurement space. In our our measurement, we have the error covariance. So it represents how much uncertainty from the previously predictions yeah that is observed in the measurement space. And of course we have the measurement noise covariance matrix that basically represent the uncertainty in the sensor measurements. If it's larger, meaning that our measurement is less reliable. So it's not that accurate, our measurements, yeah. And then we have our residuals or called innovations. So why the residuals is called innovations? It's basically giving new information. That's why it calls innovations. It combines basically uncertainty from both the predicted states and the measurement noise. And this one, yeah, the predicted state and the measurement noise, right? And it basically reflects the total uncertainty in the difference um, between the predicted measurements and the actual measurements. All right. So yeah. And then we have the state updates. So we chip in our Kalman gain here. And the residuals or the innovations is basically our differences between the what observed, what we observe or what we measured, and what the Kalman filter predict to our measurements. And our Kalman gain will incorporate that and then see how the relevance is between both. Yeah. So it's basically called innovations because it indicates how much the new information of our new current state provides about the state. So yeah, if the predictions align with observations, then we'll be having zero residuals, right? So in here, so yeah, in here. So if our predictions is somehow the same like measurements, if our ZK is somehow the same like this one, if our measurements is somehow the same like predictions, then we'll be having zero and then the Kalman will be zero. So our estimations our update estimates will be somehow the same like our previously estimations. But if our measurements or if our observations have residuals, then of course we'll be having the Kalman. We have to put Kalman update here, Kalman gate update to our initial estimations, and later on we'll be having updated estimates. And the covariance updates is also somehow the same. Yeah, we incorporate our covariance or our uncertainty between measurements and the predicted covariance matrix beforehand. And then if we have residuals, meaning that our variance is somehow uh, not aligned, but uh, if we don't have residuals, mean that our covariance is somehow the same, then we'll be having later on the updated error covariance matrix. So basically that was the general idea of how the Kalman filter works. So we have the states, then we have the predictions, and we have the updates. So that's those two things that basically has to be remembered. And the Kalman gains is basically describing the influence of how we have to incorporate our measurement to our state estimations. So for example here, the movement of AUV in the 3D motions. So we have the true paths, which is shown as a blue line. And then we have the measured data. And then we have the estimations. So as we see here, the measurement is not always aligned with the true paths, but somehow sometimes also aligns. And our estimation is somehow also not always aligned. And at the end, it basically combine both, which is the model and the predictions, and we'll be having the best estimations of our AUV. Okay, as we can see here, it might be not always accurate. So to have more accuracy, maybe we have to add more measurements to have more Kalman gain influence in our models, or correct the models at the first place. All right, so that was the techniques to do the basically to do the inertial navigation system for positionings, for velocity, or for orientations if we're having three states that we want to determine. And then the next we want to do the combinations basically, or the fusions between the external sensor with the inertial navigation system, which is the coupling. So the coupling in aided INS this basically refers to integrating the inertial measurement from the IMU with the external sensor like GPS, magneto, acoustic positioning systems to improve accuracy, right, and the robustness of the systems. And three types of the coupling in the aided INS system is loose coupling, tight coupling, or deep coupling. So here, for example, the coupling between GNSS measurement with the inertial measurements. We can change that into acoustics. For example, here in the loose coupling, the GPS provide only pseudo range measurements instead of positionings. So the inertial measurements, both of them are measuring or doing their algorithm separately. They are running their algorithm separately, and at the end we do the additive after it does the algorithm. After it runs the algorithm separately, we combine it with the adaptive tuning or Kalman filtering, and then we at the end have the GPS and INS Kalman filtering. Yeah, So the loose coupling is basically doesn't really incorporate the GPS measurements or the range measurements from the acoustic positioning systems. As the advantage is more simpler because yeah, both of the measurement are running separately, and the existing GPS or acoustic positioning system or INS can be combined with minimal integration of effort, right? Yes, basically that doesn't directly access the raw measurement of data, so only pseudo range or carrier phase, so it doesn't really like uh so the INS doesn't really integrate into the measurements of the pseudo range from the GNSS or the range from the acoustic positioning system, for example. In tight coupling, it deals with that more deeply. So the INS and the IDing systems share the raw measurements of gyros and accelerometers, for example. It shares the raw measurements of range from GNSS or from acoustic positioning systems. And the outputs are integrated together with the extended Kalman filter. So instead of range measurement from only or motions measurement from the gyro and accelerometers, we'll be having the range measurement from the acoustic positioning system in tight couplings. Yeah, and then we have the deep coupling or ultra tight coupling, deep coupling. This is more complex because it's fully integrated with the INS. It's allowing both systems to influence each other internal operations, basically in real time. And the INS and the aiding system, like for example here the GPS, share a single processor. So it's basically yeah, process in one computer unit, for example, or deeply integrated framework. So if it's not in the uh, if it's installed in the different sensor, like we always use in the observer positionings, it's deeply integrated. So like in the AUV, it has its motherboard, and this motherboard is deeply integrated the framework between the USBL, for example, DVL with the INS. For example, the INS, the inertial measurement can assist in DVL signal tracking by stabilizing weak signals, for example, and for GPS signals, it can also refine the INS solutions. And yeah, of course, it's more robust, more accurate because it's fully integrated. So was loose coupling was loosely integrated. We don't share the raw data. In tight coupling, we share the raw data, but it's not like fully integrated. And in the deep coupling, it's fully integrated, which is more robust, more complex, and yeah, and more computational demanding. So in the loose coupling, its sensor operates independently, and the measurement from the sensor are fused at the end. So for example, DVL are measuring the range and having positions, and then our gyro and accelerometers are measuring the velocity, positions, and orientations. And for that parameters, the four parameters are later on chipped in together. And as we know, we'll be having also the innovations. The predictions will be having predictions, and then the INS times velocity, for example. And then for update, we'll be incorporating with the Kalman gain, where the Kalman gain, as we know, determines how much weight to give to the SPL corrections. So it's basically the Kalman gains here is not the kalman gain influence is small because the USPL and the, for example, the AINS is not fully integrated as in the tight coupling or deep coupling. In tight coupling, the sensor data is fused in the real time before updating the vehicle states. So before we know our vehicle estimations or vehicle position, our AU positions, we fuse our measurement together. Then with the kalman gain as well, where the kalman gain is updated at each time steps based on both the process noise from the AINS and the measurement noise from the USPL. So we incorporate basically both of the acoustic position system and the AINS. We'll be having better estimations, but still it's not like fully aligns with the true values of our designated AUV positions. What's the better? Because in the loose coupling, we'll be having, like, for example, drift, but in tight coupling, we'll be having better estimations. And deep coupling or ultra tight coupling is, in addition to the sensor fusions, the sensors basically influence the state estimation process more directly and more frequently, interacting with each other at each step in a more complex manner. With kalman gain being larger for deeper fusions and the process noise covariance for AINS might be reduced to emphasize the USPL measurement. So it's basically we want to emphasize the USPL measurement more here in this case. So this is, for example, the comparison between loose coupling, tight coupling, and deep coupling. As we can see here, the deep coupling is having better estimations in comparison with the loose coupling and the tight coupling, right? So the deep coupling has somehow more closest estimation to the true value in comparisons with the tight coupling and loose coupling. Even though our AINS has drift and yeah, our USPL is not always incorporated every time, but by combining both of the sensor, we'll be having the closest to the true values. Right, then we'll go to the applications of the AINS, the Aided Inertial Navigation Systems. For example, this is, as I shared earlier about the autonomous pipeline monitoring, that is the ongoing project in the University of Hamburg, which is the CM project. So basically, why detecting the pipelines? So it's because pipeline allows for continuous transport of crude oil or natural gas or cables. Like, for example, there are 900 kilometers of thin fiber optic cables under the sea, carrying 99% of international data. So, like, for example, for internets and also other connections, mean for that. And nowadays, the threats for pipelines and undersea cables, because of the war and human caused threats, for example, ship anchors, fishing activities, wars, and natural threats like water movement, corrosion, sediment stresses, and also the age of the pipes, which is important for us to monitor that. And it requires a lot of time to monitor all of the pipes together. That's why we have to accelerate the monitoring by using the autonomous underwater vehicle or the AUV. So, for example, if there are minor damage to the pipeline, it can lead to the pipeline accidents, so the oil will be leaked, and because of the leakage of the pipelines, it leads to the enormous ecological and economic damage. So that's why the autonomic and continuous monitoring is necessary. So for example, here, deploy the AUV from surface, from one positions, for example, and it autonomously track the pipelines along the way. And after it collects the pipeline and reach the position B, it will ascend again and transmit the data in the docking. But yeah, it has to detect the pipeline and track the pipeline autonomously. And after it process some transacts, it will tell the system that it will go up and time to transmit the data or collect the data or send the data to be post-processed. And the AUV can be charged in the docking platform, and then later on can be continuous, can be deployed continuously to another transacts, for example. All right. So as a remarks for AINS or for sensor fusions, of course, if we are talking about the offshore positionings, we cannot rely only with one systems for doing our navigation solutions underwater, because we don't have the global reference frame for that, as this is available for GPS. For example, here the INS should be integrated with TVL or USBL updates from the main ship, or LBL that installed underwater updates from the installed beacons. And then we do the sensor fusions either with a Kalman filter or extended Kalman filter with real-time state-based estimations. So it's, yeah, the INS basically provide the accelerations, orientations, positions. TVL provide the velocity, and the coordinates provided by the acoustic position systems, and we chip in all of them together to provide the better real-time state estimations. Yeah, sometimes the connection through man's ship or sea surface is necessary, and acoustic connections is also somehow required, which limits our applications. So the USBL should be, if you're using USBL, meaning that the mothership should be available. But if you're talking, you want to install only the docking platform, it's somewhere on the port so that the AUV can navigate between one port to another port. So for example, the AUV want to go from Jakarta, Surabaya, and then we don't have to deploy it from our main ships all the time offshore. We only want to deploy the AUV autonomously every time. It will fully autonomous, like it will go autonomous from the docking platform in Jakarta, and then it will go autonomously track the pipeline along the way until Surabaya, and then recharge and found the docking in Surabaya, and then doing that autonomously. And then we in the office will just have the data and then doing the maintenance if there's a problem or alarm that creates by the AUV. So yeah, that will limit our application if we have to rely on the acoustic transponder under the seabeds, or the acoustic that has to be installed on the motherships at the first time. And then the equations, basically, if we're talking about the filtering, the most common way is doing with the Kalman filter that combines the noisy measurement with the noisy predictions or flow predictions to create the optimal state estimate later on. And we can use the covariance as a measure of how much uncertainty there is in the noisy measurement and also the models. And for final estimation, because both of the Gaussian uncertainty or the Gaussian variations or the covariance, we multiply of them together, and then we'll be having the final uncertainty, which is also Gaussians. Since the covariance is multidimensional, it's mathematically easier to maintain it in a matrix form. So it's basically all the calculation of matrix, but sometimes it gets larger and larger because we have a lot of state factors like positions have 3 parameters, orientations have 3 parameters, duration we have 3 parameters, and if we incorporate it with another USBL, right, we have range, DVL, we have range, and later on we'll be having a really big matrix. And if you're doing it every time, we'll be really having a big matrix. But yeah, still easier to display the matrix rather than another form. So basically the concept of Kalman filtering uses 3 different covariance metrics: measurements, model, and the final estimations. So we basically dealing with uncertainty to doing the estimation. So in order to maintain the estimates of the system state, so in order to maintain as low as possible the covariance, so that we can be sure that our estimations at the end is okay for our AUV. And the error mitigations can be done with the coupling that integrate the AINS basically, right? So as we can see here, the USBL position fix is coupled with from measurement from the AINS and the USBL. So on, we'll be having best estimations for AUV. All right. I think that's all. Well, maybe it's not too details, only brief discussions about how we can do the aided inertial navigation system, but of course we can get the general overview of how if you want to do the offshore positioning, so of course we cannot rely only with one systems, and we have to rely with integrations of the sensor or sensor fusions. And sometimes we do it with Kalman filtering, but another filtering techniques can be also incorporated. So yeah, basically in positionings we deal with uncertainty, and we cannot really trust ourself, even though we estimate in a good values. But of course, maybe the measurement can also have the uncertainty. So our estimation can be flawed and our measurement can be noisy, and then the combination between them can be also more noisy or maybe less noisy. So we have to do it like iteratively. So if you really want to have a good estimation later on, you have to do it iteratively, because our measurement is basically a lot, and our predictions can be also updated in a lot of time. So yeah, at the end we have a lot of iterations for doing this estimation from that simple equations to have the best estimations of our positions. All right, I think that's all. Thank you for the attentions. Yeah, and see you in the next lectures.